Hello and welcome to Lecture 2 of Momentum and Impulse in Phys 1101. And in the last lecture we met impulse. In this lecture we're going to meet momentum. And at this stage it's not going to look very useful. It's going to look more or less like a calculational trick. Momentum will come into its own in the next lecture when we look at how to use it to analyze collisions. So here's a sort of situation that often arises. You've dropped a ball. And because you know how far you dropped it, it's easy to figure out how fast it was going just before it hit the floor. But the collision with the floor is very complicated, and unless you have really high-speed video, it might be difficult to determine how fast the ball was going after it leaves the floor. However, it's often relatively easy to measure forces over short time scales. There are things called force plates and various other things you can use to do this. So I'm going to define up as positive for y. This is going to be the force by the floor. And the thing is, of course, typically that wouldn't really be a triangle. It might be some sort of a curvy shape like this, right? But you could approximate it as a triangle, and the nice thing then is that you know how to calculate that area, because we've just seen that the area under the force versus time graph is this thing we call the impulse, which is equal to the average force times delta t. And this is going to turn out to be useful. So if we want to get this VF, we can use this. So let's calculate this area. It's a triangle. Right? And so it should be a half base times height. And that base is 10 milliseconds. Be careful of units, right? You always want to work in seconds, kilograms, and meters. And the height is 180 newtons. Now let's just look at the units here. A newton is a kilogram meter per second squared, and we're multiplying that by seconds, so seconds take out seconds, and we're going to get an answer that is in kilogram meters per second, and it's going to come out as 0.9 kilogram meter per second. Okay, so what? Well, let's do a trick. This is F av delta t. And by Newton's second law, we know that F av is ma av. So there we've got ma av delta t is j. And we know j, we've found it. And now we'll do another trick. Ma av, well, a av delta t, that's delta v, right? And so we've got m delta v is j. Delta v is vf minus vi, so I can just solve this and I'll do a bit of the algebra in my head. You can pause the video and verify this if you wish. This is what you would come up with. And now note I've made up positive, so this is a positive force, right? This is the floor pushing off the ball. Think about that. I'm being a little bit sneaky and ignoring something. And vi is negative, 5 meters per second down, negative. So VF is 0.9 kilogram meters per second over 0.1 kilogram, right? That's the 100 grams. Kilograms are gone. Minus 5 meters per second. And that comes out plus 4 meters per second. 4 meters per second up. I just did a few sort of tricky things, so let's go back over them. I solved for the velocity after the bounce using the impulse, which was the area under the F versus t curve. And just by the definition of what we mean by average, that is the average force times the time of the collision. And then we used Newton's second law to turn that F av into an ma av. And then finally, we looked at this a av delta t and recognized that from the definition of an average acceleration, we can turn that into a delta v. And so in the end, I had a way of getting vf straight out of the area under the F versus t curve as long as I knew vi. So this is a trick. although we're going to see there's more to it than a trick. But before we go on, let me just point out a few things that we're ignoring at the moment. So first of all, these are all vectors, right? And I've totally ignored that through this, but it was a one-dimensional problem, right? The ball was going straight down and then the ball was going straight up. So this is just like being all the way back in Unit 2 of the course. And we'll do this for a while, but we will put back in the vector nature of all of this and think about how that affects impulse and so on. But the other thing was a little more tricky. This F_av that I gave you was the force of the floor on the ball, or in other words, a normal force. But here I'm saying F_net. Am I just being sloppy? Because of course this ball would have also had a weight on it, and I completely ignored that. So let's look at what in fact was going on if we think about the weight as well. So during the fall, the only force acting on the ball was its weight. And we know how this plays out. We know that this leads to an acceleration that is just g down, right? We get F_net is just W equals ma, so ma equals mg, a equals g. But during the bounce, we've got this normal force acting up, and that's really what this is. This is really the normal force on this graph. And the complicated thing was that it's varying. However, I just totally ignored the weight because I said that F_av was equal to ma_av, and I used this force. But that's not strictly right? Because this should be F_net, and I've just ignored the weight. So let's see whether that was reasonable. So we can easily calculate what the weight was, right? We know that the weight is just mg, and so that is 100 grams, right? That's 0.1 kilograms times g, which is basically 10, right? And that's a newton. But the force due to the floor, the normal force, is much larger than that. And in particular, if we want to know the average, so let's just look at the average normal force, right? So that is equal to the area under the curve. And so N_av delta t, this is J, right? And we found what that was. That was 0.9 kilogram meters per second. And so that's J. So N_av, the average normal force, was just 0.9 kilogram meters per second over delta t, which was 0.01 seconds. That's 90 newtons. So just compare those and notice that the normal force on average is almost 2 orders of magnitude bigger than the weight. And so we're going to make only a very small error by neglecting the weight. So let's just look at that argument again. During the fall, the weight is the only force acting on the ball. It's 1 newton, but it is what is causing the acceleration of the ball. It's the only thing causing the acceleration of the ball, and so it would be very strange if we were to neglect it. But during the bounce, things are different. Now the normal force due to the floor is 90 newtons on average. The weight is still 1 newton. Now, notice the weight hasn't changed, but we can neglect it because it is so small compared to the normal force. And we're only going to make an error of about 1% by neglecting it, right? It's only around 1% of the size of the normal force. And so if we just ignore it in F_net, we're only making an error of 1 part in 90. So as long as we don't need precision of better than 1%, we can go ahead and do that. So just look at that argument that I've just made, because it's an argument that's important to understand. Things are negligible when they're small in comparison with other things. We're not talking about the absolute size of things that we neglect. We're talking about whether they're negligible in comparison to other things. But then beyond that, whether something is negligible or not depends on what precision you need. If you're neglecting something that causes you to make a 1% error, well, if you need better than 1% precision, then you shouldn't do that. But much of the time, we don't need that sort of precision. So we've been using this equation that the impulse is m delta v, or m times vf minus vi. And so apparently this quantity m times v is sort of useful. So this is what we're going to call the momentum. We'll represent it by p, I guess because m was taken for mass, right? So a momentum is just a mass times a velocity. And we'll talk more about how to think of a meaning for it later. So we can now write our equation for impulse as a delta p, a change in momentum. The impulse equals the change in momentum. And this is called the impulse momentum theorem. But recognize where it came from. All we did was we started with F equals ma, and basically we've just multiplied both sides by delta t, and we've wound up with this. So really, the impulse momentum theorem is just another form of Newton's second law. Let's do a little experiment, and many students find the outcome of this experiment a little bit surprising. So what I have here is two boards that I'll set up in a moment, and what's in my hand here is just a wad of paper that I'm making wet. And you see the blue thing here is a rubber ball, so I am going to make the wet paper the same mass as the ball. There, so now it's balancing with the rubber ball. And so I have a ball and a wad of wet paper that are roughly the same mass. And now I'm taking these two boards, and you see the markings on the boards, and I'm going to line them up so that they're hanging off the edge of the table by the same amount. And now what I'm going to do is I am going to drop the ball and the wet wad of paper onto the ends of these boards. Now, the ball, of course, will bounce, and the wad of paper is going to go splat and not bounce. And remember that they have the same mass, and I'm dropping them from the same height, and so when they hit the boards, they're going to be going down at the same speed. Now, I've arranged it so that one of them is going to knock its board off, and the other one won't. So you now need to decide which is which. Will the ball knock its board off, or will the wet wad of paper knock its board off? And I'll warn you, if you think using impulse and momentum, this will be easy. And if you don't, you probably will guess wrong. So, here's your question to think about. And if you're in my course, then you'll be asked this on Moodle. And if you aren't in my course, then I would encourage you just to pause before you go on to the next video to find out the answer.